Hello everyone, I hope you are safe and well. We are happy to present our paper in CRV 2020. Let me start with just a few words about myself and my background. My name is Askhat and we are from Nazarbayev University, Kazakhstan. I work as a research assistant and pursuing my master's degree in computer science. In this presentation, we'll be discussing image classification techniques based on graph embedding. Moreover, we will show our approach for the image classification task using the distortion-free graph embedding and KNN-Random forests. Image classification is the task of classifying an image into a class category. It is the most well-known computer vision task. Famous benchmarks include the MNIST dataset for handwritten digit classification and ImageNet, a large-scale image dataset for object classification. Since the successful use of AlexNet for image classification, deep neural networks such as VGG, Inception, ResNet, DenseNet have become the dominating approach for this task. Furthermore, deep neural networks have shown their ability to learn more representative and discriminative features for image classification. Classification based on graph embedding has been actively studied in many frameworks. Traditionally, these approaches represent images using handcrafted features and construct graphs where vertices show features and edges encode relations between the features. The approaches then perform graph embedding into some geometric space such that similar graphs are located nearby while dissimilar graphs are placed further away. As you can see, it is possible to represent an image as a graph and find a similarity metric based on the Earth mover's distance between two graphs. Then, it is possible to use this representation for a variety of tasks such as content-based image retrieval, image labeling, image classification, etc. Extracting discriminative and representative features has been a fundamental task in computer vision for decades. One of the popular ways of handcrafted feature extraction is using scale-invariant feature transform, so-called SIFT, which has been successfully applied to a number of problems such as object recognition, panorama stitching, and 3D modeling. However, recent deep learning approaches have become a very popular tool for image classification, which can automatically extract features, learn, and classify them. Therefore, a deep learning architecture such as convolutional neural networks can be used as an automatic feature extractor by using a squashing function and encoding. This means that instead of extracting handcrafted features, we can extract deep features and apply a graph embedding approach as it was shown in the previous slide. In this paper, we've proposed a novel framework based on distortion-free graph embedding using deep features and KNN-Random forest. Our framework consists of 6 main steps. In the first step, there is a fine-tuning of a pre-trained deep learning model for the dataset. Then, extracting deep features for each image and sort them in descending order by their stability value computed in the deep learning model. Thirdly, we create a complete graph such that each node represents a feature and the weight of each edge reflects the absolute difference between the corresponding feature values. It is followed by the embedding of each graph into a geometric space under L-infinity without distortion. Finally, applying the hybrid algorithm KNN-Random forest for image classification and generating the classification output. We have performed our large-scale experiment using VGG19 model for ImageNet datasets with a subset of its classes. The features extracted without a fine-tuning of VGG19 aren't a good set of representative features since the original VGG19 model has been trained on 1000 classes instead of 10. Therefore, the transfer learning technique has been applied. Constructing a graph with this simplified version is computationally less expensive. In our case, we selectively train some of the last layers, not only just replace the final layer. This allows us to represent an image with a fewer number of deep features compared to VGG19. To be more precise, we have frozen the last 2 layers of VGG19 and added layers of 200 and 150 nodes respectively. This variation significantly helped from the computational standpoint because we do not need to store all 4096 VGG19 deep features but only 150 features for properly representing an image. The majority of problems in different real-world applications could be transferred to a graph-based problem. Graphs are applied in different domains like chemistry, social networks, molecular biology, and computer networks due to its ability to capture hierarchical feature relations and its invariance to viewpoint changes. Analyzing graphs leads to various methods of graph representations. In particular, after obtaining deep features from an image, we sort them in descending order based on their values and construct a fully connected graph. The distance between nodes is computed as the absolute difference between the features. This distance is also known as a Chebyshev or a chessboard distance, i.e. the distance between points x and y is computed as is shown in the slide. Future ordering is one of the most important parts of the embedding process, since this embedding is very sensitive to the order of the features. The previous work using this embedding order features by their relative position with respect to their neighbors, which is both costly and error-prone. In the proposed framework, we simply use the values as computed in the deep learning model. This ensures the stability of our ordering process. In addition, since there is always the same number of features obtained for an input image, we do not deal with the problem of equalizing features, unlike the previous work. Inspired by the idea of a hybrid algorithm for classification tasks, SVM-KNN combination has been successfully used as an image classifier. It has been shown that SVM-KNN applied large multi-class datasets outperforms both KNN and SVM individually. The main principle of this algorithm is to use the hybrid SVM-KNN in the following way. Firstly, applying the KNN and label the query if and only if all k neighbors have the same label. Otherwise, apply the SVM and get the query label. Using a similar idea, we employ KNN-Random forest as the image classifier in this paper. Here, random forest is used as a replacement for SVM. KNN suffers from the problem of high variance, while SVM is computationally expensive. A crucial reason for this replacement is due to the computational requirements of SVM, especially for large datasets with a number of classes. And now we come to the experiments. We have used a subset of an ImageNet where each class is represented with 1000 to 1500 images per category. To increase the number of images in our dataset, we have used data augmentation, which artificially expands the size of a training and testing datasets by creating modified versions of all images in the dataset. This technique improves the ability to generalize for a model by feeding new variations of images. Particularly, we use a rotation of 20 degrees and the horizontal flip for each image, creating additional 5 variations per image in the dataset. Figure 1 shows this data augmentation where the first image in each row is the original image, whereas the rest presents the transformed images for the classes Violet, Tarantula, and Cheetah, respectively. We use a subset of ImageNet such that the total number of images is around 70k and the split proportion of the training and testing is 80 to 20, with 57k images used for training and the rest for testing. Another popular family of approaches for graph embedding is based on the concept called caterpillar decomposition, which is the set of the edge disjoint root to leaf paths. Caterpillar decomposition introduces a distortion, i.e. the distances in the embedded space aren't exactly equal to those in the graph space. However, a distortion-free graph embedding under L infinity using handcrafted features obtains better image classification scores. Although powerful, this approach needs to equalize the size of the input graphs and orders the vectors to properly apply the embedding. These steps are both error-prone and limits the applicability of the technique in practice. By using deep learning features, the proposed approach doesn't suffer from these problems. The experimental evaluation of this paper includes a comparison with the caterpillar decomposition. We should note our results are based on top 1 accuracy rather than top 5 accuracies mostly reported by the state-of-the-art methods for ImageNet. Recall that the best performing model based on the self-training method is EfficientNet L2, achieved 87.4% of the top 1 accuracy on the entire ImageNet. Although we have used a subset of the dataset, the results still indicate the important potential of the proposed work. In order to evaluate the classification framework based on the distortion-free graph embedding using different datasets, an experiment using STL10 has been conducted. STL10 consists of 5,000 training images with 10 predefined folds, which are similar to CFAR10 with a size of 96 to 96 pixels. Furthermore, there are 100K unlabeled images in the dataset. However, unlabeled images aren't utilized in this experiment and purely based on the labeled 5,000 images part. Our method outperforms the state-of-the-art graph embedding-based image classification approach for the task of image classification. Particularly, the proposed framework obtains 97.5% top 1 image classification accuracy for the ImageNet dataset for 5 classes and 93.3% for 10 classes. Also, STL10 top 1 result is 90.79%. Graph embedding techniques have been employed by several different frameworks for a number of problems such as image classification, feature correspondence, and image indexing. In this paper, we have proposed an image classification framework based on distortion-free graph embedding with deep features. Although such distortion-free graph embedding has been proposed with handcrafted features before, the way that we apply this embedding using deep features, overcoming some problems faced by the alternative technique, is novel. We have shown the effectiveness of the proposed framework using STL10 and the subset of an ImageNet. However, our future goal is to perform a more comprehensive evaluation in a larger dataset and compare it with more alternative methods. Finally, I'd like to thank the co-authors who have helped me in this project and to the grant from the Nazarbayev University. And thank you for your attention.